Previously, we've discussed the idea of rate of change. Specifically, we talked about the average rate of change of a function. And in this video, we're going to talk about how we can move from the average rate of change to the instantaneous rate of change. To do that, we need to remember this idea here. The idea that the rate of change of a function is the same thing as the slope of the function. And when we were talking about average rate of change, we said that the average rate of change of a function is the same as the slope of a secant line. So what we'd like to do is, rather than look at what a function is doing over a period of time, over an interval, we want to look at what it's doing at a particular point. So we'll start this video with an example. This is a very similar example to one we did in another video. And basically what we want to do is we want to find the rate of change of this function f of x over the interval from a to a plus h. Now if you remember in our previous example, we used a as our left endpoint and then we chose h as the width of our interval. So we take our left endpoint and add on the width to figure out what the right endpoint is going to be. We also did a similar example to this where we let the right endpoint be a second variable. In that case it was b, and we did the same type of thing. The difference here is the function we're going to use is just f of x. We're not going to use any particular function. We're going to leave it as general as we can at this point. So let's first look at what the points, our endpoints of the interval are going to be. The left endpoint will have an x value of a and a y value of f of a when we plug in a, and the right endpoint will have an x coordinate of a plus h and a y coordinate of f of a plus h. So what we're looking at here is the average rate of change from the left endpoint to the right endpoint. And to do that, we will use the slope formula, where the slope is equal to the difference in y's over the difference in x's. And so the difference in y's here will be f of a plus h. Remember, we like to use the second coordinate first, the second point first in the slope formula. So we're subtracting f of a plus h minus f of a, and that's going to be over the second x coordinate, which is a plus h, minus the first x coordinate, which is a. So we have a plus h minus a. The only thing in this difference quotient that can be simplified is going to be in the bottom here. And if you note that we have a positive a and a minus a, those two will cancel each other out, and all we'll have left in the denominator is h. So this turns into f of a plus h minus f of a all over h. And what we have here is a general formula for any function f for the rate of change, the average rate of change over the interval starting at a and with a width of h. Now we talked about we want to move from average rate of change to instantaneous rate of change, so we're going to look at how we can take this difference quotient here and make it into something useful as far as instantaneous rate of change goes. So I've been calling this thing a difference quotient. This difference quotient right here is something we're going to see over and over and over again in calculus as we get into the idea of the derivative. And it's exactly what we got out of our last example. It's the average rate of change of the function f starting at a at the left endpoint and with a width of h. So let's look at what's going to happen here numerically. If you remember that difference quotient, f of x plus h minus f of a plus h minus f of a all over h, what we have on top is the difference in the y's, which we're looking at over here. The difference from point A to point B along the y-axis is delta y, or f of a plus h minus f of a. For this particular function, we're going to look at a specific function here. For this particular function, that difference is 15. And on the bottom, we have the difference in x's, which is just the width of the interval from a to b. That width is h, so delta x is going to equal h, and for this particular example, it's going to be 3. So what we have here then, this blue line is a secant line, since it intersects the function twice. The slope of that secant line is the change in y over the change in x, which is, this is backwards here, should be 15 over 3, which is 5. And I think these are all going to be backwards, so I will replace those as we go. So the change in y is 15, the change in x is 3, and that's going to give us a slope of 5. Now, if we move b a little bit closer to a, and I'll say right now, ultimately what we want to do is we want to find the slope of the tangent line at a, which will look something like this, touching the point at a, and make that look a little bit better. So we're looking for the slope of that line. So to do that, what we're going to do is we're going to take this point b here and we're going to slide it closer to a, and we're going to see how close we can get it. So moving b half the distance, we've got the same type of thing here. We can find the difference in y's by subtracting the y values, find the difference in x by subtracting the x values, and again, I made a mistake here. This should be 8 over 2, which is then going to give us 4. And moving b even closer, you get 3 over 1, which is 3. And moving b even closer, we get 1 1/4 divided by 1/2, which is 2 1/2. And moving b even closer and closer, we end up with values that are approaching the instantaneous rate of change. So what we're doing here is we're making this delta x super, super small. And as a result, the delta y is also getting really small. And so we're getting numbers that are really small over really small, and they're approaching a value. In this case, it should be 2.21 over 0.1, which is going to be 2.1. And if we were to look at these values in a table, we would see that they're approaching a particular value. Here we made delta x even smaller, or h even smaller, but they're approaching a particular value. In this case, they're approaching the value of 2. And so what we have here is a picture of what's going on here. We looked at secant lines as we move this second point closer and closer and closer, and the slope of that secant line is getting closer and closer and closer to the line that we actually want, which is this tangent line in blue right here. And so what we're going to do is we're going to use the idea of a limit, and we're going to take that average rate of change and we're going to turn it into an instantaneous rate of change. So again, remember that the average rate of change is the same as the slope of the secant line, so the instantaneous rate of change is going to be the same thing as the slope of the tangent line. So in a problem, if I ask for instantaneous rate of change, then what you're really trying to do is you're trying to find the slope of the tangent line at that point. So let's go back and look at this difference quotient one more time. This difference quotient, again, is the average rate of change over the interval starting at a and then with a width of h. What we want to do is we want to make that width really, really small. So the slope of a curve at a point, which is the same thing as the instantaneous rate of change, is the limit of this difference quotient as that the width of that interval goes to 0. So we're going to make that really, 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 really small until it goes to 0, and this limit here, if it exists, is going to give us the instantaneous rate of change.